Maybe waiting for a flight at the airport. You see that free public Wi-Fi and you connect. I mean, we've all done it a million times, right? But did you ever get that little feeling in the back of your mind like, who else is on this network? Could someone be, peeking over your digital shoulder? Well, that exact worry is the problem that a VPN was born to solve. So what's the solution? Well, think of it like this. You build your very own private armored tunnel that cuts right through that public internet highway. And yep, that's our virtual private network, or VPN. The name really tells you the whole story. It's virtual because, hey, it's using the same public internet we all share. But, and this is the magic part, it's private because everything inside that tunnel is locked down with encryption. It creates a secure, totally confidential connection from your device to its destination. It's basically your own personal armored car on the information superhighway. Pretty cool, huh? And the benefits here are just huge, especially for businesses. We're talking massive cost savings compared to the old days of leasing private lines. You get that rock-solid security because of encryption. It's incredibly easy to grow. Just add another user. And it works on pretty much any internet connection you can find. It's a really elegant solution to a lot of big business needs. Okay, but here's the thing. Not all of these tunnels are built for the same job. Let's peel back another layer of this onion and look at the two main reasons you'd use a VPN, either connecting individual people or connecting entire places. And this is a really crucial difference. On the one hand, you have remote access VPNs. These are for people. This is you in that coffee shop clicking connect on your VPN app. You are actively creating a temporary secure tunnel back to your company's network. You know it's happening. On the other hand, you have site-to-site VPNs. These are for places. Think of this as a permanent, always-on bridge connecting a company's New York office with its London office. To the people working inside those offices, everything just works. They probably have no idea their data is zipping through a secure tunnel. So it's people versus places, a really fundamental distinction. So we get what a VPN is and what it's for. But how does it actually do all this? What are the actual tools in the toolbox that make this secure tunnel possible? Let's dive in. Okay, let's go back to that remote access scenario. You in the coffee shop. You've basically got two main options. First up is an SSL VPN. The big selling point here is simplicity. You can connect securely from almost any device using just a web browser. Super convenient. Then you have the powerhouse, the IPsec VPN. This one needs you to install specific software on your device, but the payoff is that it secures all of your internet traffic, not just what's in your browser. So really, it comes down to a classic trade-off. Do you need easy, convenient access, or do you need comprehensive total security? Now we're getting to the heart of it all. How does a VPN actually keep your data secret and safe? It's time to look at the secret ingredients that make the security part work. The real workhorse behind most modern VPNs is a technology called IPsec. But here's the thing, IPsec isn't just one single protocol. It's really a whole framework, a collection of tools and rules that all work together to build that secure tunnel we've been talking about. And this toolkit has 4 jobs that are absolutely essential. First up, confidentiality. This is the locked box. It uses encryption to scramble your data, so it's complete gibberish to anyone trying to snoop. Second, integrity. This is like a tamper-proof seal on a package. It guarantees that the data you receive is the exact same data that was sent with 0 changes along the way. Third, authentication. Think of this as the secret handshake. It proves that you are who you say you are and that you're talking to the right server. And finally, key exchange. This is the super clever, super secure process for deciding on the secret encryption codes in the first place. You need all 4 of these pillars for a truly secure VPN. Now, let's focus on that first pillar, confidentiality, for a sec. It's not a one-size-fits-all thing. As the source material says so well, the degree of confidentiality depends on the encryption algorithm and the length of the key. So what does that actually mean in practice? Well, this chart says it all. On the left, you've got an older standard, like DES, and on the right, you have a modern one, like AES. That huge difference in the key length, the number of bits, means that AES isn't just a little more secure. No, it is exponentially harder to crack. We're talking billions of years for a computer to guess the key. It's the gold standard for a reason. And what about that tamper-proof seal we mentioned, the integrity part? That's handled by something called HMAC. It's a bit technical, but the idea is simple. It takes your original data and runs it through a special math problem to create a unique digital fingerprint. If anyone changes even one tiny little bit of that data while it's in transit, the fingerprint on the other end won't match, and the system knows instantly that it's been messed with. It's a guarantee that what you get is what was sent. So after going through all of that, what's the real secret here? What's the big idea you should walk away with about what makes a connection truly secure? It all boils down to this. A secure connection isn't just about having a tunnel. It's about what that tunnel is made of. It's that powerful framework, that combination of confidentiality, integrity, authentication, and key exchange, all working together inside the tunnel that provides real, meaningful security. And now you know exactly how it all works. All right, today we're putting on our detective hats. We're about to solve a classic IT mystery, piecing together an entire network map when all you have is a single point of entry. So let me paint you a picture. You've been tasked with documenting a network in some remote office. You can get into one device, but beyond that, it's a total black box. I mean, where do you even start? Well, that's the exact challenge we're going to solve right now. Your mission, should you choose to accept it, is to draw up a complete map of this remote branch. But there's always a twist. You also have to track down one specific switch that's been plugged in but never configured. It has no IP address, which makes it pretty much a ghost to most of our standard network tools. Okay, so first things first, we gotta get in. We start from our own PC and SSH into our local gateway. Easy enough. From there, we make the jump across the internet to the remote office's main router. We pop in the credentials and we're in. We've landed on a device called Branch Edge. This is where our investigation begins. And this is where things get tricky. The tools we just used, like SSH, or even something simple like a ping, they all need an IP address to work. Our target, that unconfigured switch, it doesn't have one. It's totally off the grid. So how in the world do you find a ghost in the machine? Well, we're going to need a special tool for this job, and that tool is the Cisco Discovery Protocol, or CDP. This is our secret weapon. See, it works at layer 2, which is kind of like the local neighborhood level of the network. It lets devices that are physically plugged into each other chat and share info. No IP address required. Here's a great way to think about it. Normal network discovery at layer 3 is like sending a letter. You absolutely have to have a specific postal address or it's not going anywhere. CDP, though, that's like leaning over the fence and just talking to your next door neighbor. You don't need their street address, you just know they're right there. Now, for security reasons, CDP isn't always turned on by default, so before we can start listening for clues, we have to make sure our main investigative tool is actually running, right where we are, on this branch edge router. And we're going to do this the smart way, the secure way. We jump into configuration mode and use CDP run to turn it on for the whole device. But, and this is super important, we immediately go to the interface that's facing the public internet and turn CDP off there. We only want to be chatting with our own internal devices, not broadcasting secrets to the entire world. Okay, our tool is active. It's secure. It's time to start listening. Let's see what this branch edge router knows about its immediate neighbors. The hunt is officially on. We run our first command, show CDP neighbors, and boom, right away we get a hit. We see a device called branch firewall is plugged into our gigabit 0/0 port. We don't have its IP yet, but we have a name. This is our very first lead. To get that IP address, we got to dig a little deeper. So we run show CDP neighbors detail. And this not only gives us the IP we need to jump over to that firewall, but it also tells us something else really interesting, the exact software version it's running. Now, for us as a detective, that's just a clue. But for a security admin, that's a potential red flag if that version is old and vulnerable. So we use that IP, we SSH into the branch firewall, and we run the exact same command again. And this is how we follow the trail. The firewall says, yep, I see that branch edge router you just came from. And it also reveals a brand new device, a switch named SW-BR-Floor2. Let's keep going. We grab the IP for switch bra floor 2 from that detailed output, and we make our next jump. See how this works? Each hop takes us deeper into the network, one step closer to solving the big mystery. And once we're on switch BR floor 2, we hit the jackpot. This switch looks like it's the heart of the whole office. It sees the firewall we just left, but it also sees two other switches, switch BR floor 1 and switch BR floor 3. Our network map is really starting to come together now. But hang on a second. Let's not forget our primary mission. We're not just mapping, we're hunting for that one specific device, the one with no IP address. We've got two new switch names here. Could switch-BR-floor1 be our target? How can we know for sure? And this is the aha moment. We run that detail command one last time, focusing on the entry for switch bridge floor 1. And there it is. Or, well, there it isn't. All the other information is there. The platform, the port, what it's capable of, but the line for the IP address is just blank. We found our ghost. You see, without CDP, this device would have been completely invisible. But by just following these layer 2 breadcrumbs from one device to the next, we found it. We know its name, and we know where it's connected. Case closed. And here it is, the ultimate payoff. This is the complete network map for that branch office. We started with access to just one single router, and using nothing but CDP and a little bit of detective work, we built this entire thing from scratch. So why is this so powerful? I mean, it's not just about finding one missing switch. This technique lets you build accurate network documentation when there isn't any. It helps you troubleshoot connection problems by confirming, yep, that cable is definitely plugged in there. And, like we saw, it's a security tool that can expose devices and software that might need an urgent update. And that really leaves us with the final thought. CDP is just one kind of digital breadcrumb that our network devices are constantly leaving behind. It kind of makes you wonder, what other clues are floating around out there, just waiting for a good digital detective to find them?
All right, today we're going to tame some chaos. We're diving into the nuts and bolts of how network engineers keep the absolute wild frenzy of the internet in check. Let's get into it. I mean, just stop and think about it for a second. The internet is basically one giant, non-stop global party. You've got trillions of conversations all happening at the exact same time. So what keeps that from just becoming a complete and total mess? How do you make sure the right data gets where it's going and the wrong data gets stopped right at the door? Well, the answer is actually pretty simple. At its heart, the internet relies on a concept we all understand, a bouncer. Now, obviously, this digital bouncer has a more technical name. It's the foundational tool that network admins use to control the flow of traffic and, basically enforce the rules of the road on their corner of the internet. And it's called an access control list, or ACL for short. You can literally think of an ACL as the bouncer's official rulebook. And it's not just one rule, it's a whole list of them in a super specific order that a router, which is kind of like the traffic cop of the internet, has to follow to the letter. So what's on this bouncer's to-do list? Well, first off, they keep the party from getting too crowded by limiting traffic. It makes everything run faster. They also provide a basic layer of security, keeping the known troublemakers out. They control the traffic flow so you don't get digital traffic jams. They also act like a doorman for a VIP room, deciding who gets to access a specific service. And they can even give priority to certain guests, kind of like letting them skip the line. So our bouncer has a rulebook, but how do they actually use it when a piece of data shows up at the door? Well, it all comes down to checking the guest list. And every single rule on that list, every line item, has its own name. It's called an access control entry, or an AC. And each AC has one and only one simple instruction. Either let it in or keep it out, permit or deny. So here's how it works, and this is really important. A data packet shows up, the router lets the very first rule on the list. Is it a match? Nope. Okay, on to rule 2. Is that a match? And it just keeps going right down the list. But here's the crucial part. The very instant it finds a rule that matches, it stops. It does what that rule says, permit or deny. And it doesn't even look at the rest of the list. The order is everything. So what if a packet gets to the very end of the list and it hasn't matched a single rule? Well, there's a secret, invisible rule at the bottom of every single ACL. It's called the implicit deny. And it basically says, deny everything else. This is a huge deal in security. If you're not explicitly told to let something in, the default is always to block it. If your name isn't on the list, you are not getting in, period. All right, so we get the list and we get the whole top-down process. But what kind of information is the bouncer actually looking at? How are they checking these digital IDs? Well, there are 2 main ways. First up, you've got the standard ACL. Think of this as the simple check. The bouncer only looks at where you came from, your source address. They're just asking, who are you? And that's it. It's basic, it's fast. Then you have the extended ACL. Now this is the detailed check. This is the full background check. The bouncer looks at who you are, where you're going, and even why you're here. Like, are you trying to browse the web or send an email? This gives you incredibly specific, granular control. Now, you can probably imagine that checking every single digital person one by one would be crazy inefficient, right? especially if you want to apply one rule to a whole group of people, like an entire office. So how does the bouncer handle that? They use a wildcard. And to make things even easier, there are two simple keywords that act like shortcuts. The host keyword is like telling the bouncer, hey, I'm looking for this one specific person's ID. It matches a single exact address. Then any keyword, and it's pretty much what it sounds like. It tells the bouncer to just ignore the ID check for this rule and apply it to absolutely everyone. Okay, so we've got our bouncer, we know the rules on their list, but where you decide to station that bouncer is just as critical as the rules themselves. The placement is totally strategic. For those really detailed extended ACLs, the ones checking who, where, and why, the rule of thumb is to place them as close to the source of the traffic as you can get. Why? Because you want to stop that unwanted traffic right at the front door before it even gets a chance to wander through your network and waste your bandwidth. It's just way more efficient. But for the simple standard ACLs, you do the complete opposite. You place them as close to the destination as possible. So why the switch? Well, because a standard ACL is a blunt instrument. It only checks where traffic is coming from. If you put it near the source, you might accidentally block that traffic from getting to other places it's supposed to go. By putting it right at the door of the final destination, you make sure it only blocks traffic trying to get to that one specific place. So as we start to wrap this up, it becomes pretty clear that access control lists are way more than just some technical jargon. They are the invisible fundamental gatekeepers that make a functional, secure internet actually possible. So let's boil it down. What are the big takeaways here? First, ACLs are the internet's digital bouncers, and they use a sequential list of rules called ACEs. Second, the order of those rules is everything, and if a packet doesn't match a permit rule, it gets denied, no questions asked. And finally, remember the placement. Powerful, extended ACLs go near the source for efficiency. Simple, standard ACLs go near the destination for precision. And all of that leaves us with one final, bigger thought. These simple lists of permit and deny, they're the building blocks for digital borders, for security policies, for everything. They control who gets access to what. And that leads to a much bigger question, doesn't it? In a world that is so completely built on access, who gets to write the rules for the gatekeepers? Welcome to The Explainer. Today, we're diving into the invisible toolkit that network managers use every single day. It's the secret sauce that keeps our digital world, from your morning newsfeed to your late night streaming, from completely grinding to a halt. You know, imagine walking into an office building with thousands of rooms, but there's no map, no directory, not even any room numbers. That's pretty much what a network administrator faces all the time, this huge unseen space. So how do you even begin to manage something you can't physically see? Well, the very first step is to draw a map. Right, so before you can manage anything, secure anything, or fix anything, you just have to know what's there. The first job, always, is to map out this unseen digital landscape. Often, a network without any documentation is just a big black box, a tangled mess of routers and switches and cables. To make any sense of it, you need that map. But how do you draw one for a world where all the connections are invisible? Simple. You get the devices to introduce themselves. Okay, so one of the first tools you'd grab for this job is the Cisco Discovery Protocol, or CDP. The best way to think of it is like a digital census taker. On a Cisco network, it basically has each device periodically shout out to its neighbors, hey, I'm a router, this is my name, and here's exactly how you're connected to me. But what happens if your network isn't just one big happy Cisco family? I mean, a lot of them aren't. That's where LLDP comes in. Think of this one as the universal translator for device discovery. It does the exact same job as CDP, but it's vendor neutral. That means a Juniper device can talk to a Cisco device, which can talk to an HP device, and so on. So you've got two fantastic solutions to the same problem. In an all Cisco world, CDP is kind of the native language. It's super easy, it's on by default. But when you've got a mix of different brands, LLDP becomes the common language, the standard that lets every single device cooperate to build that crucial map together. All right, so we have our map. We know what's on the network. But to coordinate anything, every device needs to agree on one critical thing. What time is it? What do you think happens when they don't? You get total chaos. Without a single source of truth for time, trying to figure out the cause of a problem is just impossible. Was that traffic spike the cause of the breach, or was it a symptom of the crash? You honestly can't tell. It's like trying to solve a mystery when every clock in the building is wrong. The solution is so elegant and absolutely essential. It's called the Network Time Protocol, or NTP. This is basically the network's atomic clock. It's a protocol that lets every single device sync its internal clock with one central, authoritative time source. It ensures the entire orchestra is playing to the exact same beat. Now, this system works as a hierarchy, which is really clever because it distributes time without overwhelming the main source. At the very top, you have stratum 0. These are your ultra-accurate sources, like GPS clocks. They pass the time down to stratum 1 servers, which then pass it to stratum 2, and on and on. Each level, or stratum, makes sure that time is distributed accurately and efficiently across the whole network. Okay, so our network is mapped out, and all our devices are perfectly synchronized. That's fantastic. But is it healthy? I mean, how do you keep an eye on the health and performance of thousands of devices all at once without actually going crazy? Well, the answer involves two tools that work together, kind of like the network's eyes and ears. First, you have SNMP. This is your proactive tool. It's like glancing at your car's dashboard. You're actively checking things like CPU usage and memory. Then you have syslog, which is reactive. That's your check engine light. A device will actively send you an alert when a specific event actually happens. So how does SNMP actually work? It's a pretty simple system of questions and answers. You've got a central manager that asks the questions, an agent on each device that knows all the answers, and a sort of library called the MIB where all that information is stored. Now with syslog, and this is really important, not all alerts are created equal. Messages are categorized by severity, from a level 0 emergency, which means the system is literally unusable, all the way down to a level 7 debugging message. This is huge because it lets an administrator instantly filter out all the noise and focus on what truly matters right now. So even with perfect mapping, synchronized time, and constant monitoring, things can still go wrong. A device could just have a hardware failure, or a critical configuration file could be accidentally deleted. So what's the plan for when disaster strikes? This is where the network admin's insurance policy comes in: backups. A key piece of advice is to always back up two things: the device's operating system, which is called the iOS image, and its specific settings, which are stored in the configuration file. And the process is surprisingly simple. It's almost like creating a save point in a video game. With a single copy command, an admin can send a router's entire brain, its configuration, to a central server. If that device fails, the configuration can be slapped onto a new one in minutes, not hours. It's a lifesaver. But what about the ultimate human error, the one that can lock you out of your own kingdom? You've forgotten the password to a critical router, and now you can't get in to manage it or fix it. What do? I mean, this is a high-stakes problem. Without the password, a perfectly good piece of hardware is basically a brick. But thankfully, the engineers who designed these systems, they totally anticipated this exact scenario. They built in a physical, last resort procedure to get you back in. And here it is, the ultimate failsafe. It's a very precise physical sequence of steps. You actually interrupt the boot process, tell the router to completely ignore its saved configuration file, the one with the password you forgot, and then once you're in, you can load that configuration back up, change the password, and restore everything to normal. It's basically the network equivalent of picking your own lock. So there you have it. This isn't just some random list of acronyms, right? It's a complete logical toolkit. You use discovery to build the map, you use time synchronization to correlate events, you use monitoring to watch for problems, you have backups to prepare for disaster, and you have a recovery procedure for the ultimate mistake. Together, they bring order, visibility, and resilience to any network. These tools, they're working silently in the background all the time, and they are the foundation of our modern digital world. So the next time you browse a website, stream a show, or send a message, just remember this invisible toolkit and the network architects who use it every single day to keep everything and everyone online. Have you ever wondered why some company networks just completely crash during a big product launch, while others can handle millions of users without even breaking a sweat? Well, today we're pulling back the curtain on the blueprint for designing networks that don't just survive the future, they're actually built for it. So, what is the secret? I mean, how do engineers build these massive, seemingly invincible networks for huge, while other smaller ones just crumble under pressure? That's the big question we're going to tackle today. The truth is, a modern network is basically a company's central nervous system. It's not just for sending emails anymore, it's carrying what we call converged traffic. That means everything, voice calls, video conferences, critical business apps, it's all sharing the exact same digital highway. These are mission critical services, and if that highway gets jammed up, the whole organization just grinds to a halt. The stakes are incredibly high. Okay, so to manage all that complexity, you absolutely need a plan. And thankfully, there's this time tested framework that brings a real sense of order to all that chaos. It's called the hierarchical model, and it's this really elegant 3-layer blueprint for building a network that's logical, reliable, and just makes sense. It all starts right here at the access layer. Now, I want you to think of this as the on ramp to your network superhighway. It's the place where every single end user device, we're talking your laptop, your office IP phone, the wireless access points, it's where they all physically connect into the system. This is the front line. All right, next up, once all that traffic gets onto the highway, it hits the distribution layer. And you can think of this layer as the network's really smart traffic cop. I mean, this is the brains of the whole operation. It takes all the traffic coming in from those different on-ramps, sorts through it, and starts making smart decisions, applying security rules, prioritizing really important data, and directing everything exactly where it needs to go. And then, sitting at the very top, we have the core layer. This thing is the backbone. It is the Autobahn of your network, and its only job is raw speed and pure reliability. It doesn't get bogged down making complex policy decisions. It just moves massive amounts of data from one area to another as fast as humanly possible. This layer is all about high-speed, super reliable transport, period. Now, here's the thing. You don't always need all 3 layers. For these huge, sprawling campus networks, yeah, the classic 3-tier design is perfect. But for smaller offices, or maybe just a single building, you can use what's called a 2-tier or a core design. All that means is the jobs of the distribution and core layers get combined into one. It's just way more efficient and cost-effective when you don't have that massive scale to deal with. So we've got the blueprint, but let's be honest, a blueprint is totally useless without solid engineering principles to make it strong. So let's talk about the key concepts that make a hierarchical network not just organized, but truly resilient and ready to scale. The first principle, and maybe the most important, is redundancy. This is your safety net. The whole goal here is to eliminate any single point to failure. And you do this in 2 main ways. First, you install duplicate hardware for your critical devices. And second, you create alternate physical paths for the data to travel. So if one switch dies or a cable gets cut by accident, traffic just seamlessly reroutes through the backup. The network stays on. Simple as that. But what about speed? I mean, how do you increase your bandwidth without having to go out and buy a ton of expensive new hardware? Well, that's where this really clever technique comes into play. It's called link aggregation, or you'll often hear it called ether channel. It basically lets you bundle a bunch of physical connections, let's say 4 standard network cables, and then it tricks the network into seeing them as one single, super fast logical connection. And you can see the power of that idea right here. A single link might give you, say, 1 gigabit per second of bandwidth. But by bundling 4 of them together with ether channel, suddenly the network sees it as one massive 4 gigabit per second pipe. You've literally quadrupled your speed just by being smart with the connections you already have. It's pretty amazing. Okay, so all these design principles don't just exist in a vacuum, right? They're built on real physical hardware. So let's talk about the workhorses of the network, the switches, and how you go about choosing the right ones for the job. Picking the right switch is really a careful balancing act. Of course, you have to think about cost and port density, how many devices do you actually need to plug in? But you also have to think about features like power over Ethernet or PoE, which is crucial for running things like IP phones or wireless access points. And most importantly, you have to plan for scalability so you're not stuck ripping it all out and replacing it in 2 years. It's all about matching the hardware to what you need now and what you think you're going to need in the future. Okay, let's pull all these different threads together. We've talked about the blueprint, the core principles, and the hardware. Let's just take a moment to summarize the core philosophy behind designing a network that is genuinely built to last. So what's the bottom line here? Look, a hierarchical design brings order to chaos. Redundancy is your insurance policy against things breaking. Link aggregation is kind of your secret weapon for boosting speed without breaking the bank. And it's all built on making smart hardware choices that balance today's needs with tomorrow's growth. If you get these things right, you've built a truly scalable foundation. And if you take just one thing away from all of this, let it be this really powerful idea: a failure domain. That's just the area of a network that gets affected when something goes wrong. A really great design doesn't just move data around, it contains problems. It limits the blast radius, so one faulty device in one little department doesn't bring the entire company offline. That, right there, is the ultimate goal. Which, brings us to our final question for you to think about. When you look at the networks you rely on every single day, are they well-designed assets that are actually enabling productivity and growth? Or are they fragile liabilities, just one broken link away from total failure? The difference, almost always, comes down to design. All right, let's dive in. Today, we're talking about the invisible revolution that's powering pretty much our entire digital world. We're going to go on a journey from these big, clunky physical machines to the super elegant, intelligent software that runs everything, from your favorite streaming service to massive global businesses. And it's a story that answers one really big question. We all throw that term around, the cloud. But what is it really? Is it just a bunch of computers humming away in a warehouse somewhere? Well, yeah, kinda. But the real magic, the real revolution, isn't the hardware itself. It's the brilliant software that makes all that hardware sing in harmony. And today, we're going to pull back the curtain and see exactly how that happens. So, to understand where we are now, we have to start with where we've been. Let's rewind the clock to the early days of the internet, when the whole digital world was built on a very, very physical foundation: dedicated servers. Think about it for a second. If you wanted to run a website, you needed a physical server. An email system, yep, that needed its own separate physical server too. Every single service was permanently bolted to one specific piece of hardware. It was a simple model for sure, but as you can probably guess, it was incredibly inefficient. And this was the heart of the problem. One application was shackled to one server. That meant all of that server's processing power, its memory, its storage, all of it was dedicated to a single task, whether it actually needed it at that moment or not. This created some massive, massive headaches. First off, you had what people called server sprawl. You had data centers just filled with these machines that were sitting idle most of the time, just burning electricity and taking up space, which also meant they were massively underutilized. But the biggest problem, the real scary one, was this single point of failure. If that one piece of hardware died, your website, your email, your entire service, poof, it was just gone. Clearly, this couldn't last. A better way was desperately needed. And that better way, the first true game changer in this story, was virtualization. This idea completely changed our relationship with computer hardware forever. Okay, so the big idea behind virtualization is actually pretty simple. You just break the direct link between the software, the operating system, and the physical machine it's running on. Instead of one OS for one machine, this simple but kind of idea opened the door to running many independent operating systems, all on a single piece of hardware. So how's this magic trick performed? With a special piece of software called a hypervisor. Now, you can think of the hypervisor as like a traffic cop for the service resources. It creates this abstraction layer that sits between the hardware and all the operating systems, and it intelligently carves up all the physical resources, the CPU, the memory, and hands them out to multiple independent virtual machines. And the benefits? Oh, they were immediate and they were enormous. Costs just plummeted because you needed less hardware, which meant less power and less physical space. Need a new server? Instead of waiting weeks for a physical box to show up, you could spin one up in minutes, literally minutes. And that whole single point of failure thing, gone. If a piece of hardware was about to fail, you could just move the virtual machine to another healthy server with zero downtime. Total game changer. But you know how it is. You solve one big problem and another one tends to pop up. We had fixed the server problem. Our servers were now flexible, they were agile, they were efficient, but the network they were all plugged into, it was still old-fashioned, rigid, and very physical. And this created a whole new kind of traffic jam. Suddenly, you had these virtual machines that could be created, deleted, or moved from one physical server to another in the blink of an eye. The network, however, was designed for static things that stay put. Having to manually reconfigure physical switches and routers every single time a virtual machine moved was a complete nightmare. It was slow, it was complex, and it totally defeated the point of having a flexible server environment in the first place. And this created a completely new traffic pattern. See, traditional networks were built for north-south traffic. That's data going from the data center out to the internet. But virtualization caused this massive explosion of east-west traffic. That's virtual machines constantly talking to each other inside the data center. Old network designs were not built to handle this constant internal chatter. Okay, so we had made our servers smart with virtualization. Now it was time to do the exact same thing for the network. The solution was another revolutionary idea: software-defined networking, or SDN for short. The big idea behind SDN is so elegantly simple, you separate the network's brain from its brawn. In a traditional switch or router, the part that thinks, that's the control plane, and the part that does the actual work of moving data, the data plane, are locked together in the same physical box. SDN breaks them apart. It pulls the intelligence out and centralizes it. So, the control plane, that's the brains of the operation. It's the part that holds the map and makes all the smart decisions. It knows the best path for data to take, and it understands the entire layout of the network. The data plane, on the other hand, is the muscle. Its only job is to be incredibly fast at doing one thing: forwarding packets of data. It doesn't need to think, it just executes the orders that it gets from the centralized brain, the control plane. And that's the key right there. With SDN, you have one central software controller that acts as the brain for the entire network. It has a complete top-down view of everything, and it can tell every single switch and router exactly how to handle every piece of data. The network becomes programmable. So what happens when you put all these pieces together? Well, when you combine flexible, virtualized servers with a programmable, software-defined network, you get the foundation of the modern, automated cloud that we all rely on every single day. And this isn't just theory. Companies are building incredibly powerful systems based on these exact principles. A great real-world example is Cisco's application-centric infrastructure, or ACI. It's a solution that's purpose-built with hardware and software to fully realize this vision of an automated data center. A really key part of ACI is its use of an advanced network design called a spine leaf topology. In this modern setup, every server is just one hop away from every other server. This creates a super predictable, low latency path that is just perfect for handling that massive amount of east-west traffic that all those virtual machines create. And here is the ultimate payoff. The network becomes application aware. So instead of an administrator having to manually configure hundreds of switches and rules, you just define what your application needs in a policy. The intelligent controller then automatically programs the entire network to deliver exactly what's required. It completely flips the old way of doing things on its head. And that's the entire journey in a nutshell. We moved from a world where software was trapped by rigid, dedicated hardware to a world where intelligent software defines and controls everything, creating the flexible, on-demand digital infrastructure we now call the cloud. It's a really powerful transformation, isn't it? And it leaves us with a fascinating question to think about. As more and more of our infrastructure, from the servers to the network itself, becomes pure code, what's the next physical boundary that software is going to completely dissolve? Today, we're going to pull back the curtain on the technology that connects our entire world, the Wide Area Network, or WAN. We're going to see how a huge company connects its main office to a tiny branch on the other side of the planet, and now that exact same tech is what brings the internet right to your screen. It all starts with a pretty basic problem. The network in your house or your office, your local network, it can only go so far. So the big question is, how do you securely and reliably connect to another network that's across town or even across an ocean? While the answer really comes down to understanding the difference between two key ideas, the LAN and the WAN. Basically, one is the network you own, and the other is the network you pay somebody else to use. Okay, let's get into it. So here's the simplest way to think about it. Your LAN, or local area network. That's your private space. It's super fast and it connects all the devices in your office or your home. But a WAN, a wide area network, that's the service you subscribe to that links your private LAN to other LANs, anywhere in the world. Think of your LAN as your house, and the WAN is a highway system that connects all the houses together. You know, the best way to really wrap your head around how this technology developed is to see it in action. So we're going to follow the journey of a fictional company we'll call Span Engineering. We'll watch them grow from a tiny startup into a global powerhouse and see how their network had to evolve right along with them. So back in the early days, Span Engineering opens its very first branch office across town. Now they needed a totally reliable, private, always-on connection between those two offices. And the solution they found was the original form of WAN technology, a dedicated physical wire. This is what's called a leased line. It's almost exactly like having your own private road built directly between your two offices. It's always there, it's just for you, and you pay a service provider a monthly fee to, well, rent the road. Okay, so let's trace the actual physical path your data takes. It starts at your office router, then it hits something called the demarcation point. That's basically the official handoff spot where your network ends and the provider's begins. From there, it travels over the local loop, sometimes called the last mile of cabling, all the way to the provider's central office, which then connects you to the rest of the world. Now, you might be thinking, this sounds pretty great, right? These dedicated lines were simple, high quality, and always on. But and this is a big but, they had some major drawbacks. They were unbelievably expensive and totally rigid. You paid for a fixed amount of speed whether you used it or not. As Span Engineering started to grow, this model became a huge problem. So that crazy high cost and complete lack of flexibility, it forced the entire industry to find a smarter way to do things, to move data over a shared network instead of a private one. And this right here is the game-changing shift. The old lease lines, they used what's called a circuit switch model. Think of an old school telephone call, where the line is kept open just for you the entire time. The new way is packet switching. Your data gets chopped up into tiny little pieces called packets. Each packet is like a package sent through a global delivery service. They're all going to the same place, but they might take different routes through the shared network to get there. It makes the whole system way, way more efficient. This whole new way of thinking just opened the floodgates for new technologies. Now, some, like frame relay and ATM, are pretty much legacy tech at this point. But something called multi-protocol label switching, or MPLS, was an absolute revolution. MPLS lets service providers connect to companies' offices really efficiently all over their shared network. You can think of it as a super smart traffic management system for all those data packets. So as SP Engineering kept expanding and went global, another network became the really obvious choice for their WAN. I mean, why build out a complex private network when you could just use the biggest public network in the world, the internet? And using the internet for your WAN meant you could use common, much more affordable broadband technologies to connect your offices. Yeah, we're talking about the same stuff many of us use at home. But as you'll see, each one comes with its own trade-offs. Let's break those trade-offs down. DSL, which runs over old phone lines, has one big issue. The farther you are from the provider's office, the slower it gets. Cable, which uses TV lines, is fast, but you're sharing your connection with your neighbors. So during peak hours, things can really slow down. And then there's fiber, which is incredibly fast, but it's just not always available to install everywhere yet. Okay, but wait a second. This brings up the next huge challenge for Span Engineering, and really for any business. If you're sending all your sensitive private company data over the public internet, how on earth do you keep it secure? The solution is the VPN, the virtual private network. A VPN creates a secure, encrypted tunnel for your data to travel through the public internet. It's like building a private armored passageway that runs right through the middle of that public highway, totally protecting your data from anyone else on the network. So all of this brings us right back to today. And what's cool is that the same principles that connect SPN Engineering's global offices, that local loop, the packet switching, the broadband connections, those are the exact same things that are powering your connection to the world at this very moment. Seriously, whether you're connected through cable, or blazing fast fiber, or DSL, or even just cellular data on your phone, you are accessing the world's largest, most complex WAN every single day. You're a part of this massive, interconnected global system. And really, this quote just nails it. When you get right down to it, the story of the WAN is a story of adaptation. It's a technology that has been constantly evolving, always driven by our growing need for faster, more reliable, and more secure connections to anywhere in the world. So the main takeaway here is that a WAN isn't one single thing. It's a whole toolkit, from those old school private lease lines to secure VPNs running over the internet. But the fundamental goal has never changed, to shrink the world and connect all of us across any distance. Which of course leaves us with a pretty fascinating question for the future. As our demand for data just continues to explode with things like AI, 8K streaming, and the Internet of Things, what will the next generation of global connectivity even look like? That's the question that's driving the next chapter of the WAN. Thanks so much for watching.
All right, let's talk about one of the internet's biggest unsung heroes. It's the reason your phone, your laptop, and your smart TV can all be online at the exact same time, using just one Wi-Fi connection. You're using it this very second, but I bet you've never even heard its name. Today, we're diving into network address translation, or as it's better known, NAT. Now, seriously, just think about that for a second. You've got that one single cable coming into your home from your internet provider, and yet you've got a whole bunch of devices, maybe a dozen or more, all streaming, gaming, and browsing the web all at once. How on earth does that actually work? It feels like it should be impossible, right? Well, that's the magic trick we're going to pull back the curtain on today. So to really get why NAT even exists, we have to rewind a bit. Because back in the day, the internet was facing this massive existential problem. A problem that could have stopped its growth dead in its tracks. We were, and this is not an exaggeration, literally running out of internet. See, the internet's original addressing system, the one we still mostly use called IPv4, it had a built-in hard-coded limit. It could only ever create about 4.3 billion unique addresses. Now back then, that probably sounded like an astronomically huge number, right? But even by the 90s, people were starting to do the math, and yeah, it wasn't going to be enough, not even close. And there's the kicker. The entire global system was designed with fewer unique addresses than there are human beings on the planet. Forget about every person having a phone, a laptop, a watch. The system couldn't even handle one device per person. This looming disaster has a name: IPv4 address exhaustion. And fixing it, well, that was going to take some serious ingenuity. Okay, so the engineers got creative. They basically invented a two-tiered system. You've got your public IP address. This is like your home's mailing address. It's totally unique in the entire world. Anyone can find it. But then they created private IP addresses. Think of these like an office number inside a giant skyscraper. Office 101 is only unique inside that one building. The building next door can have its own Office 101, and it's no problem. It's a way to reuse addresses on a local level. And this is exactly where NAT comes into the picture. So if your home network is that office building, and all your devices are the individual offices, then NAT is the super efficient receptionist sitting in the lobby. It's their job to handle all the incoming and outgoing mail, acting as that single critical link between your private little world and the huge public internet. So what is NAT officially? Well, it's a process, and it's happening right there on your home router. It takes all the requests from all your different private devices, and then it sends them out to the internet using that one single public IP address. It's basically a translator or a proxy, making a whole crowd of devices look like just one single person to the outside world. Okay, but how does the receptionist not get everything mixed up? It's all about amazing records. So let's break it down. Your laptop sends a request. Our receptionist, the router, grabs it, swaps out the private office number for the public mailing address, and here's the most important part. It jots down a little note in its logbook. Hey, this request came from the laptop. Then, when the response comes back from the internet to the main address, the router just looks at its log, goes, this one's for the laptop, and sends it to the right place. Simple, but brilliant. All right, so as you might guess, it's not quite that simple. NAT isn't just one thing. It actually evolved over time into a few different flavors, each one built to solve a slightly different kind of problem. First up, you've got static NAT. This is the most basic version. It's a permanent, one-to-one mapping. Think of it like giving one very important person in the office their own dedicated public mailbox that never changes. This is super useful for things like a company's web server, right? You need a stable, predictable address so that customers and clients on the outside world can find you every single time. Then there's dynamic NAT. This is a bit more flexible. Now, instead of permanent mail slots, our receptionist has a small stack, a pool of public addresses they can hand out. When someone in the office needs to send something, they get an address from the top of the stack. When they're done, it goes back in the pile for the next person. The only problem? If you run out of addresses in your pool, any new devices just have to wait. It's first come. And that leads us to the billion-dollar question, the one that actually matters for your home network. What happens when you have a dozen devices, but only one single public address to share between all of them? How can you be on a video call while someone else is streaming a 4K movie at the exact same time? Well, the answer is a truly brilliant upgrade to NAT called Port Address Translation, or PAT. Some people call it NAT overload, but whatever you call it, this is the superpower. This is the real secret sauce that makes your home Wi-Fi actually work. It's an absolute game changer. Okay, look closely, because this is where the magic happens. PAT is clever because it doesn't just look at the IP address. It adds another piece of information, a port number. Think of the public IP as the building's street address and the port number as the specific apartment number. So as you see here, two different private devices both try to send something out using the same port, 1444. Our router, the receptionist, sees this and says, whoa, that's going to get confusing. So for the second device, it cleverly changes the outgoing port to 1445. Now, when the replies come back, one to apartment 1444 and one to 1445, the router knows exactly which device to give them to. It's genius. So NAT is pretty brilliant, you have to admit, but we've got to remember what it is at its core. It's a patch. It was always meant to be a clever workaround, not a permanent solution. And just like any quick fix, it comes with its own set of pros and cons. So on the plus side, well, the big one is that it literally saved the IPv4 internet from grinding to a halt. Huge win. It also gives you a nice little bit of security because it hides your whole internal network from prying eyes. But on the downside, all that translating back and forth adds a tiny bit of lag. It also breaks something called end-to-end traceability, which can make troubleshooting some network issues a real headache. And yeah, it can sometimes mess with certain protocols. Okay, so if NAT was just a temporary fix, what's the permanent one? And what happens to NAT when we finally move into the future of the internet? Well, the real permanent fix is something called IPv6. And the number of addresses it provides is just mind-boggling. We go from 4.3 billion to 340 undecillion. That's a 340 with 36 zeros after it. To put that in perspective, that's enough IP addresses to give one to every single atom on Earth, and you'd still have incomprehensible amounts left over. So yeah, in a pure IPv6 world, the whole reason we invented NAT in the first place, to save addresses, it just vanishes. But here's the catch. Switching the entire internet over is taking a long time. So for now, the old IPv4 internet alongside the new IPv6 internet. And to make sure they can talk to each other, we, you guessed it, use another special translator. It's called NAT64, and its whole purpose is to be a bridge translating between the old and new systems so nothing breaks while we're in this long, awkward transition phase. When you step back, NAT is just a fantastic story of engineering on the fly. It's a clever, pragmatic fix that really held the internet together for decades longer than it should have lasted. It really makes you think, doesn't it? What brilliant, maybe slightly imperfect workarounds are we building into our tech right now that people will be talking about decades from now? What's the next NAT? Something to think about. Thanks for joining me. Welcome to The Explainer. Today, we're digging into something called quality of service, or QoS. You've probably never heard of it, but it's the invisible traffic cop of the internet, and it is the only reason your modern digital life actually works. Okay, let's just start with a situation that I'm sure we've all felt. You're in an intense online game, everything's on the line, and bam, lag hits. Everything freezes. Well, that's not random. There's a traffic jam happening right inside your home network. And to really understand why, we've got to look at how that traffic actually moves around. All right, so the first thing we have to do is stop thinking about the internet as some kind of magical, fluffy cloud. A much better way to picture it is as a massive system of highways. And just like the roads you drive on every day, these digital highways can get seriously jammed up. And that's the root of all our problems, congestion. It happens when your internet connection, your own personal on-ramp to the digital highway, gets flooded with way more data than it was built to handle. That 4K movie and your online game are all trying to squeeze through the same tiny pipe at the same time, and this creates some pretty nasty side effects. The first problem you'll notice, something called jitter. So imagine your data travels in these tiny little pieces called packets. Think of them like a convoy of cars. Jitter is what happens when that convoy gets all broken up in traffic and the cars start arriving at their destination out of order and at weird intervals. On a video call, this is what makes someone's voice sound all robotic and choppy. The pieces of their words are literally arriving in the wrong sequence.
But then it can get even worse. You can get packet loss. This is when the traffic jam gets so bad that your router, which is trying to direct all this traffic, just gets overwhelmed and starts, well, throwing packets away. They just vanish into thin air. In a voice call, this creates those awful silent gaps where it sounds like the line went dead. That's because parts of the conversation weren't just delayed, they were completely deleted.
Okay, so if all this data is causing these epic traffic jams, what's the solution? Well, it starts with a pretty simple realization. On a real highway, an ambulance with its sirens on is way more important than a regular delivery truck. The exact same thing is true for our digital highway. The trick is making the network smart enough to tell the difference. So let's break this down with a really easy analogy. Think of a voice call, like on Zoom or FaceTime, as an ambulance. It absolutely has to get through right now with no delays. Then you've got a video stream. That's like a VIP in a limo. It's important and it needs a smooth, consistent ride to its destination. And what about an email or a file download? Well, that's our delivery truck. It's got to get there eventually, but a little bit of a delay isn't the end of the world. Now here's where it gets really interesting, because we can actually put numbers on this. Voice traffic, our ambulance, is incredibly fragile. A delay of more than 150 milliseconds and your brain starts to notice it. Video is a little more robust, but data, our delivery truck, is a totally different beast. It's built to be tough. It uses a system that's kind of like a delivery service that makes you sign for every single package. If one packet gets lost, the system just says, hey, I didn't get that one, and it gets resent automatically. That's why your file download can survive a much bumpier ride. And this slide, this really shows you the massive scale of the challenge we're facing. By 2022, video traffic, those data-hungry VIP limos, was projected to make up over 80% of all traffic on the internet. That's the new reality. Our digital highways are now completely dominated by the most demanding, most sensitive vehicles out there. So how in the world do you stop the delivery trucks from causing a total gridlock and blocking the ambulances? You can't just build a bigger highway every time there's traffic. No, you need a smarter system. You need an intelligent traffic cop. And that traffic cop is quality of service. Now, this is the most important thing to get about QoS. It is not about giving you more bandwidth. It's not making the highway bigger. It's about intelligently managing the highway you already have. It's a set of rules that lets a network play favorites, basically. It prioritizes certain vehicles over others, making sure the most critical ones always get through, even when there's a huge traffic jam. Networks can handle this in a few different ways. The default setting is usually best effort, which is exactly what it sounds like. A total free-for-all. First come, first served. Then you've got more advanced models. Integrated services is like calling ahead and reserving a private, dedicated lane just for your ambulance. But the one you see most often is differentiated services, which is like creating permanent HOV or express lanes for different kinds of traffic. One for ambulances, one for limos, and one for everybody else. So what's actually in this digital traffic cops toolkit? How does it actually do all this? How does it manage the flow of traffic and keep everything moving nice and smooth? Well, it really all boils down to three main jobs. First, the traffic cop has to be able to identify the vehicles. It needs to know an ambulance when it sees one. Second, it needs tools to manage the traffic jams when they inevitably happen. And third, and this is the really smart part, it needs to be proactive to prevent the highway from grinding to a halt in the first place. This is the foundation for everything else, classification and marking. Basically, your router looks at every single packet that comes through and figures out what it is. Ah, this is a voice packet. That's an ambulance. This one's video. That's a VIP. And then it marks or tags that packet with a priority level. Without this step, the network is blind. It just treats everything the same. So once everything is tagged, the network can start to do some really smart traffic management. On the top, you see a basic network. It's first in, first out. It is just one long line and everybody waits their turn. And yep, that ambulance is stuck right behind the slow-moving delivery truck. But on the bottom with QoS, the network can create a high-priority express lane. This lets our ambulance, our voice traffic, completely bypass the traffic jam and get through instantly. It's a game changer. And the last tool in the box is maybe the smartest one of all, congestion avoidance. This is all about being proactive. Instead of just waiting for total gridlock, the system keeps an eye on the traffic levels. As the highway starts to get full, it might strategically and preemptively drop a few of those low-priority delivery truck packets to keep things flowing. It's a small sacrifice for sure, but it ensures the highway never comes to a complete standstill.
This way, the ambulances and the VIPs can always get through. Okay, so ambulances, express lanes, packet dropping. That's a lot of technical stuff. Why does any of this actually matter to you in your daily life? Well, because this invisible system of rules is the bedrock of pretty much everything we now do online.
I mean, seriously, think about it. Without QoS, reliable remote work would be impossible. Your Zoom calls would be a choppy, frustrating mess. Telehealth appointments? No way. Trying to stream a 4K movie without it buffering every 2 minutes? Good luck. And competitive online gaming? You can just forget about it. QoS is the unsung hero that makes all of these things just work. And this quote right here, this really says it all. This is the ultimate goal. The whole point of this incredibly complex system is to create a digital highway that is so reliable, so predictable, that packet loss, those dropped pieces of your conversation or your game, is basically a thing of the past. And that leaves us with a pretty fascinating question for the future. You know, we've pretty much figured out how to manage the ambulances and the VIP limos of today. But what happens when entirely new types of vehicles hit the road? Things like fully immersive virtual reality or augmented reality streams, which are even more demanding. As our digital world keeps evolving, so too will the invisible rules that govern its traffic.
All right, let's talk about one of the absolute cornerstones of network security. We're diving into access control lists, or as you'll pretty much always hear them called, ACLs. Think about your network for a second. Every single day, it's just getting hammered with traffic, right? Some of that is totally fine, stuff you want, but a lot. So the big question, the one every network admin has to answer, is how do you sort it all out? How do you let the good guys in and slam the door on the bad guys? Well, the answer might actually surprise you with how simple it is. You hire a bouncer. Seriously. The best way, by far, to get your head around an ACL is to just picture a security guard standing right at the front door of some exclusive club. Now, this bouncer isn't looking at your driver's license, right? It's looking at data packets, and it's checking every single one for permission. This is your network's first line of defense, making a split-second decision on every single packet. You can come in, or nope, you're not on the list. So, here's the key. The ACL isn't the bouncer itself. The ACL is the rule book. It's the guest list that our bouncer, who in the real world is your router, is following to a T. It's just a list of permit or deny statements, and the router reads it from top to bottom. The very first rule of packet matches decides its fate. That's it. But, and this is maybe the most important thing to remember about ACLs, there's a hidden rule at the very end. It's an invisible line that you don't even have to write, and it says deny everything else. So if a packet gets to the end of the list and hasn't been explicitly allowed in, it's denied. The bouncer's default answer is always no. And you know, just like in real life, not all bouncers are created equal. You've got the guy who just kind of glances at a clipboard and asks, name? And then you've got this super professional security detail that wants to know who you are, who you're here to see, and what your business is. And that's a perfect lead-in to the two main flavors of ACLs you're going to run into, standard and extended. They're both trying to do the same thing, but man, they go about it in completely different ways. Okay, so let's really break this down. Your standard ACL, that's your basic bouncer. It looks at exactly one thing, the source IP address, that's it. It's basically just asking, hey, where are you from? Simple, right? But also kind of limited. Then you have the extended ACL. Oh man, this is the pro. This is the sophisticated security guard. It checks everything, the source address and the destination address and the protocol, like is this TCP or UDP traffic, and even the specific port number. It's asking the whole series of questions. Who are you? Where are you going? And what exactly are you trying to do here? So when would you use a standard ACL? Well, if you just need to do something simple, like block traffic from an entire network, or maybe allow a specific printer, and you only care about where it's coming from, a standard ACL is perfect. It's fast, it's efficient, gets the job done. But the real power, the surgical precision, comes from extended ACLs. This is where you can get super specific. You can write a rule that says something like, okay, let the marketing team access the web server over HTTPS on port 443, but deny them from accessing absolutely anything else. See that? That level of granular control is what modern network security is all about. Okay, cool. So we get what these bouncers do, but how do you actually write their rule book? It's not just random. It's a really deliberate 4-step process. All right, here's how it goes down. Step 1, plan. And I can't stress this enough. You don't just jump in and start writing rules. You have to know exactly what you're trying to permit and what you're trying to deny. Get that policy down first. Step 2 is to actually write the rules. Pro tip, do it in a simple text editor first so you can double check everything. Step 3, apply it. You have to tell the which door, which interface to put the bouncer on, and whether they're checking people coming in or going out. And finally, step 4, and this is the big one, test everything. And look, this quote from the Cisco Networking Academy is pretty much the golden rule of ACLs. Because think about it, one tiny mistake, one line out of place, and you could either take your own users out of things they need, or way worse, you could accidentally leave a giant security hole wide open. You have to test. You have to make sure your bouncer is doing exactly what you told them to do. Okay, so we've got the basics down for writing the rulebook. Now let's get into a more advanced technique. Because ACLs have this really clever trick up their sleeve that solves a super common security puzzle. So picture this. One of your users goes to browse a website. Their computer sends a request out to the internet. That's fine. But for the website to load, the web server needs to send a reply back in. So if your security policy is to block most incoming traffic, how does that reply get through? You can't just open the floodgates for all incoming web traffic. That would totally defeat the purpose of having a bouncer in the first place. So what do? The answer is a fantastic little keyword called established. This is something you can tack on to an extended ACL rule. And it's brilliant. It basically tells your router, hey, only let this incoming TCP traffic through if it's part of a conversation that somebody on the inside already started. It's kind of like keeping the main front door locked to strangers, but having a special side door that automatically swings open for expected guests. In this case, the replies to your user's requests. And as soon as that reply is in, the door shuts and locks right behind it. It's a super simple but incredibly effective way to keep things secure while still letting people do their work. All right, let's bring this all home. As we wrap up, it's worth asking again, why are these seemingly simple lists so incredibly fundamental to all of network security? So here's the bottom line. What are ACLs? They're the digital bouncers for your network. You've got two main types, standard, which is simple guest list checking, and extended, which does a full detailed security check. That established keyword, that's your secret weapon for letting replies back in safely. And please, if you remember one thing, remember this, the implicit deny. At the end of every single ACL is that invisible rule that says deny all. If you didn't specifically permit it, it is not getting in. End of story. Look, ACLs are really just the beginning. They are the solid concrete foundation that all other network security is built on. I mean, they're your first and often these digital cat burglars trying to get their hands on our most valuable information. We're going to pull back the curtain on their methods, their tools, their entire playbook. And then we're going to explore the amazing cryptographic tech we use to build defenses that are stronger than any bank vault you can imagine. Let's get into it. All right, before any good heist, what do you have to do? You gotta case the joint. And in our digital world, that means understanding the battlefield. Every system, every network has potential weak spots. So first, we need to learn the lingo, or even something like a natural disaster. It's the who or what that poses a danger. And finally, that brings us to the exploit. This is the crowbar. This is the lockpick set. It's the specific tool, a piece of code, a string of commands that an attacker uses to take advantage of that vulnerability and pop open that unlocked door. So let's put it all together. A threat uses an exploit to take advantage of a vulnerability. Simple as that. Okay, so we've got the unlocked doors and we've got the tools to get in, but who's actually holding those tools? Let's meet the crew for our digital heist story. As you're about to see, not all hackers are created equal. You know, hackers are usually broken down by the color of the hat they wear. White hats? They're the good guys. They're the security experts hired to find the vulnerabilities so companies can fix them. Then you've got the black hats. They're the classic villains of our story, breaking into systems for money, for revenge, you name it. And somewhere in the middle, they might break the law, but their motive isn't necessarily evil. Maybe they're trying to make a political statement, or maybe they just want the fame. But let's be real, the hats are just the beginning. The landscape is way more complex. You've got your script kiddies. These are amateurs, basically, using tools that other smarter people have built. Then you have hacktivists, groups who use their skills for political protest. But then you get to the big leagues. We're talking organized cybercriminals operating like businesses, all motivated by pure profit. And at the very top of the food chain, state-sponsored groups. These are digital spies and soldiers with the almost unlimited resources of an entire nation backing them. The threat level just skyrockets. So now we know the players. let's take a look at their playbook. A real digital heist isn't just some smash and grab. Oh no, it's a meticulously planned operation. And it all starts with reconnaissance. Just like casing a bank, an attacker starts by gathering intel. They'll use public tools, stuff anyone can find. Then they'll ping the network. It's like knocking on every single digital door to see who's home. Once they find computers that answer, they'll scan for open ports, which are the specific doorways into that computer. And when they find an open door, they check its locks for any known weaknesses. And then they bring out their exploit tools. It's a very methodical process of elimination, all to find that one weak spot. But you know what? Sometimes the easiest way into a secure building isn't by picking a lock or breaking a window, it's by tricking someone into holding the front door open for you. That is social engineering, the art of manipulation, because so often the weakest link in any security system is the human being. And these tactics can be ridiculously simple, and that's why they work. Phishing emails are probably the one you've seen, an email that looks legit, trying to trick you. Baiting is even sneakier. Just leave an infected USB stick in a parking lot. Someone's curiosity will get the better of them. And then you have the really low-tech stuff, like tailgating an employee through a secure door or just plain old shoulder surfing to peek at someone's password. So, the plan is set. The target's in their sights. The recon is done. Now let's see how the heist actually goes down. What do these attacks look like when they're happening? One of the most common attacks is a denial of service, or DOS. I want you to imagine 1,000 people all trying to cram through a single doorway at the exact same time. Total chaos, right? Nobody gets through. That's a DOS attack. A single source just floods a server with so much junk traffic that it grinds to a halt. A DDoS, or distributed denial of service, is that on steroids. It's the same idea, but now the traffic is coming from thousands or even millions of hacked computers all at once. It's an absolute tidal wave, and it's incredibly hard to stop. Another classic attack is the man in the middle. This one is straight out of a spy movie. The attacker basically inserts themselves secretly between you and whatever website you're talking to, like your bank. You think you have a secure private connection, but they're in the middle, intercepting everything. They can read it, they can capture it, and they can even change the messages going back and forth, and you'd never even know. All right, we've seen the criminals and their playbook. It's a little scary, I know. Well, now for the really cool part, building the vault. How do we fight back against all this? The answer is cryptography, the science of secret codes and secure communication. So any good security system, any digital vault, has three main goals. It's called the CIA triad. First, confidentiality. That's just keeping secret. Simple. Second, integrity, making sure your data is trustworthy and nobody has messed with it. And finally, availability, which just means you can actually get to your data when you need it. Every single defense we build is trying to achieve one of these three things. So let's focus on that middle one, integrity, for a second. Imagine you send this simple message to your bank. How can you be 100% sure that a man-in-the-middle attacker doesn't just change it to say, transfer $10,000 to Alex? Well, the secret sauce here is a really clever technique called hashing. You take your message and you run it through a special mathematical algorithm. And what comes out the other side is a unique digital fingerprint, a hash. You can think of it like a tamper-proof seal on an envelope. And this is where it gets absolutely brilliant. Your original message produces this very specific hash. But if an attacker changes even one single character, changes that 0 to a 9, for example, the new hash will be completely different. So when the bank gets your message, its computer recalculates the hash. If it doesn't match the one you sent, a giant red flag goes up. They know it's been tampered with. Integrity is confirmed. Okay, but what about secrecy, confidentiality? How can two people create a shared secret key to lock their conversation if an attacker is listening to every word? This is the absolute magic of the Diffie-Hellman key exchange. Let's use colors. First, Alice and Bob agree on a public color that everyone can see. Let's say yellow. Then they each pick a secret color that only they know. Alice picks red, Bob picks blue. Now they each mix their secret color with the public yellow, and they exchange those new mixed colors. So Alice sends orange, Bob sends green. Now for the final incredible step. Alice adds her original secret red to the green she got from Bob, and Bob adds his original secret blue to the orange he got from Alice. And like magic, they both end up with the exact same final color, a shared secret, without ever once revealing their private colors to each other or to the person listening in. This is literally how secure connections are made online, millions of times a day. So we've built these incredible digital vaults using cryptography, and they are getting stronger and smarter all the time. But here's the thing. The attackers, they never stop. They are always updating their playbook. So that leaves us with a final question to chew on. As our technology gets more secure, where's the next great heist going to come from? Is it something futuristic like quantum computing that will break all our codes? Or is it something much simpler, like tricking the human on the other side of the screen? The heist, you see, is never truly over. Hey everyone! Today, we're going to talk about something that's a total unsung hero of the digital world, the Network Time Protocol, or NTP. You probably never think about it, but it's this invisible force that keeps our entire digital world ticking along in perfect harmony. So let me just start by asking you this. What on earth could a regular old network router possibly have in common with a hyper-accurate, super scientific atomic clock? Well, the answer is actually the key to a stable, manageable network. And that question leads us right to the heart of the matter, what we can call the problem of time. See, before we can even talk about the solution, we've got to understand why a network device even needs a clock in the first place. I mean, seriously, right? Why does a router or a switch need to know the correct time? It's not like it's going to be late for a meeting, but the answer is absolutely fundamental to how networks run, how they're secured, and how we fix them when they break. It all boils down to one huge thing: troubleshooting. Just imagine something goes wrong with your network. You're trying to piece together what happened by looking at system logs from maybe 10 different devices. Now, if every one of those devices has a different time, well, it's a complete nightmare. You can't build a timeline. It's like trying to solve a puzzle when you've got pieces from 10 different boxes. And, it's not just about fixing things. A lot of security protocols flat out won't even work without precise time. So how do we solve this chronological chaos? Well, that brings us to the solution, the network's clock. And this is where we introduce the protocol that was designed to fix this very problem. And that solution is the Network Time Protocol. The easiest way to think about it is as the ultimate official timekeeper for the whole network. Its entire job is to make sure every single device, servers, routers, you name it, agrees on the exact same time, right down to the millisecond. And the way it works is actually pretty elegant. It uses the UDP protocol, which is just a really fast and efficient way to communicate. And to avoid any messy confusion with time zones and daylight saving, everything is based on Coordinated Universal Time, or UTC. The whole concept is simple. You have a central server that gets the time from a really reliable source, and then it just hands out that correct time to all the other devices. And the best part? It is incredibly light on the network. It only takes one tiny little packet per minute to keep a device perfectly in sync. Really, the best analogy is to picture a digital clock tower for your entire network. The NTP server is that clock tower, broadcasting the official time. And every other device on the network is like a person down on the street, just looking up at the tower to set their own watch. Simple as that. Okay, theory is great, but let's actually see this thing in action. We're going to walk through a really quick practical example to show you just how ridiculously easy it is to get this configured. So here's our little setup. We've got one server, N1, that's going to be our clock tower. And then we have two routers, R1 and R2. And these are the guys that need to get the correct time from our server. That's the whole shebang. So the first thing we do is check the status on our router. And this is exactly what we see. Right out of the box, NTP isn't even running. This means the router has absolutely no idea what the correct synchronized time is. It's totally clueless. And this just illustrates the problem perfectly. We ask the router what time it is, and it tells us it's 1993. I'm not kidding. It's just relying on its own little internal hardware clock, which defaults back to that date anytime it gets reset. It's the digital version of finding an old